shots of the exam. There's a time limit, 3 hours each time you take it, and so on. It'll go live on Thursday night. What I'm going to do first before that is instead of a classroom session like in this room, there'll be on the discussions forum, there'll be a new there'll be a new thread that says questions review for the exam. So if you have any questions on a material or homework or material that we've covered up to that point, you can ask me questions, and you can either tune in online at this time, or you can just post the question, and then you'll see it addressed in the recording from that online session. Okay, everybody all comfortable with that? Okay, so let's cover the material for tonight. Okay, so here's our current session. Let me go over what's on this material. Many of you guys, the only review of this, many of your classmates, the only review of this that they're getting is what's online, not what we're doing here, although eventually they do see this, a recording of this session as well. Okay, normal and binomial distributions, what we're going to cover tonight. In a moment, we'll talk about what that is. It's covered in both versions of text, 3rd edition, 4th edition, just a chapter apart, and the old edition is 3.1, and the new edition is 4.1 to 4.4. In the folder lecture materials, there is a recorded lecture from Levi Waldron. It's a formal lecture in which you have a PowerPoint that's being presented, principally presented as a PowerPoint on probability and a binomial distribution, on normal distribution. You should watch that. It's relatively theoretical. In other words, you'll get a lot of the background for what we're doing. So it's a bit different than what you'll see in the next section, which is basically kind of structured as a lab exercise more than anything else. Okay, so you have that. Oops. And you have lecture materials. Excuse me, I meant lab. Here we go. Okay. So in the lab exercises, you have the material that we're going to cover tonight. Okay, these are the documents, some pictures, some Excel files, and so on and so forth that we're going to play around with tonight. This material is echoed in a lecture I did earlier this week, which I have the recording up for that other class. I attached a copy here. It is in these recordings, these supplemental recordings. This first video is that lecture. Okay, it's relatively long. I have more time, much more time in that course than I have here. So it's a relatively more detailed version of what I'm going to do here tonight. So if you're not comfortable that you got everything you need from what we do here tonight, that would be worth looking at. It's literally the same material we're covering tonight. I also have here some basic information about using SPSS. Now, I was going to query you guys about where we stand on that now. What's the story on that? Do we have licenses for that yet? Still not. Okay. You have no idea, right? They have no idea when it's going to happen yet. Yeah. Well, they're not annoyed at you. I'm sure they're annoyed at the people that keep holding them off. Okay, so let's talk about what our options with that is. Okay, so we're going to have to start using SPSS. We have no choice. And in fact, most likely, I'm probably going to want to point in a problem on the exam that uses SPSS, but I'm holding that in abeyance until I know that you guys have access to it. So what can we do about that instead? Well, one way is we can bite the bullet and spend $35 and buy the program. I know how abhorrent that is, but I mean, it's like a few lattes, right? It's not that much money. So I will post information on where you can download it. There's 2 versions that you can buy. It's called the SPSS Grad Pack base version and standard version. The base version costs about $35. The standard version costs about $45. This is a program that's standalone. You would pay $800 for it. It's a ridiculously expensive professional program. So that's not a lot of money for a 6-month license for this program. The $35 version of it has everything we'll use in this course, with the exception of logistic regression. Logistic regression is kind of an advanced topic. We're going to cover regression, linear regression, multiple regression. Logistic regression is a bit more advanced topic. We're going to at least introduce it in this course. I'm probably not going to give you any problems on it. You're probably not going to get any homework or exam questions on it, but I want to at least expose you to it. Okay, if you have the base version and you can't do it, you can buy the $35 version. That's no big deal. If you want to make sure that you're able to, like, try it out, do an exercise or two with it or something like that, you might want to spend the extra $10 and go for the $45 version. Okay, I will give you links to where IBM has a site. If we Google it now, as a matter of fact, I'll show it to you now. If we Google it, you'll see they have links on their SPSS site that give you 3 locations where you can buy, 3 websites where you can buy the student versions of this program, and you can go in there and choose whichever one you think you're most comfortable with. Okay. Yes.
Did they say, like, last year we had access,
Yeah.
licenses, but should we just not
No, they told me they're trying to do it, and in the meantime, just use the virtual desktop.
Yeah.
But I think the issue is, at least I use the virtual desktop for the homework, but it's very slow, and I'd be worried on an exam losing the exam while doing the virtual desktop because it's
Maybe I'll log on to the virtual desktop here if I can and give you an idea of what it looks like when you use it. I think we might have done that last week. Yeah. Yeah, for those of you guys that didn't see it, I'll give that before we get done tonight. I'll give that a try so we can take a look at what that. So that one way is to just bite the bullet and buy it. That's one possible deal with this. Second way is use virtual desktop. That is a version of SPSS which resides on a computer in the cloud here at CUNY somewhere that you can run it on that computer. Your screen and keyboard are basically connected to that computer. The software is not actually running on your computer. Okay, it's a little confusing because when you log on to it, you actually log on to that computer. So you're basically working on their desktop and their computer. So if you want to save a file, if you want to open a file, you have to navigate to your computer, open that file, and then work on it, and then save that file to your computer, not to their computer. You have to know where you are, right, when you're working with it. That's probably the most confusing part of this whole thing. The other part that could be a little bit confusing is that in order to get it to work, you have to install a plugin or an application that allows you to access the virtual desktop. And you have to use your CUNY, I guess your CUNY first login or something like that to get to it. So at any rate, so it can get a little bit confusing. The other thing is you're doing this over the internet. So if there's any kind of glitch in the internet or something like that, or you lose connection or something like that, you're out of business. So it's a good idea to frequently save files somewhere where you know you can get to them, namely on your computer, not their computer. Because as soon as you log off with them, those files are gone, right? So it doesn't store as far as I know, it does not store your data for you. So yeah, and it's slow because now you have your connection and the connection is not from keyboard to the computer. It's not keyboard to some distant computer, and depending on how good your internet connection is and how busy they are, not always your fault. Sometimes it's stuff going on with this server. It could be a little tedious. Certainly not as good as having it on your own computer. The third possibility is that almost every computer at any CUNY location that's available to students has SPSS on it. So if you're in Midtown, you can go, if you're downtown 34th Street, you can go to the grad center there. If you're at Hunter at 68th Street, you can go to the 10th floor in the North building or whatever it is, and they have like dozens and dozens of computers that you can sit down and use. If you're here, we don't have a library here. I'm trying to think. There are a couple of labs here that have it. If you're at Silverman, you can sneak in at Silverman. I think with your School of Public Health cards, if you show them at the front desk and tell them you're here to use the library or something like that, they'll let you in. There's computers in the library, but also in the basement. They have big computer labs. So you just have to kind of check in at the guard's desk. You can't scan, it won't let you in if you just scan them. You have to just ask them to let you in. So you can go to almost any school in CUNY and sit there and use the computers. So that's another option as well. I wish I could make them speed up on this, but You know, I'm like, you know, I'm bottom of the totem pole here. I'm an adjunct. I'm not, you know, I'm not a administrator here or anything like that. So I've been around a long time. You'd think I would have more influence, but it doesn't work that way. Okay, there's a nope. Right, what is that nope about? What does that mean? I'll wait until I'll come back to that to get an answer. Okay. So you have a recording here of that lecture. And I'm going to go through this material now quickly with you, but I have less time to do it than I had there. So it's worth playing that back instead of possibly the one that I'm going to do now, although this could be maybe a quicker introduction into this material. Okay, so let me back up here. So binomial distribution or probability. Let's talk about probability. Okay, so now, you guys remember when we were talking about probabilities, we were talking about simple situations where, for instance, if I asked you if I flipped a coin, what's the probability I would get heads? It's 50-50. 0.5 is the probability you get heads. If I flipped 2 coins, what's the probability that both would be heads? Well, that was relatively simple because they're independent events. One coin doesn't know what the other coin is, whether it came up heads or tails, so it can't influence the outcome of the other coin. So the probability of both becoming heads is 0.5 and then 0.5 again, or 0.5 times 0.5. It's a multiplier. Probability of getting, if I flipped 10 coins, probability of them all being heads is 0.5 times 0.5 times 0.5 times 0.5. I know it's 0.5 to the 10th power. Okay, pretty straightforward. Well, then we said to ourselves, what about the situation where probability is not 50%? For instance, what if in a population I know that the prevalence of diabetes is 10%? What's the probability that if I picked any individual out of that population, completely randomly picked an individual out of that population, what's the probability that that person would be diabetic? As it happens, we know that would be 10%, right? 0.1. Okay, what's the probability then if I pick 2 people randomly out of that population? Again, independent events. They have no relation to one another. I completely picked them out randomly. Prevalence is 10%. What's the probability both would be diabetic? Well, just like with the coins, the probability is going to be 0.1 times 0.1, right? Or 0.01. 1 in 100 is going to be probability that they both be diabetic. What's the probability that if I pick 3 people out of that population randomly, that they would be diabetic? Be 0.1 times 0.1 times 0.1. Times, right? Okay, we'll get to ending probabilities together in a second. Okay, so great, ups 0.01, 001, 1,000. Okay, so what's the probability if I picked one random person out of that population, they're not diabetic? What's that? 0.9, yeah, it's equal to 0.9. What's the probability that if I picked 3 people out of that population, none of them are diabetic? 0.9 times 0.9 times 0.9, right? 0.81, and what would that be? 0.7, whatever, 0.7 something, right? So again, it's a multiplier, right? Because they're independent events. Okay, so that's pretty straightforward. If I had 10 people, and what the probability that none of them would be diabetic would be 0.9 to the 10th power. Just 0.9 times itself 10 times. Pretty simple. Things get a little bit more complicated when I tell you that I'm going to pick out of this population, I'm going to pick 10 people randomly, right? Completely random, right? From this population has a prevalence of 10% diabetes, okay? And I said to myself, what's the probability that I will have exactly 3 out of 10 people that are diabetic? Well, one of the reasons why it was easy for us to deduce what it would have been if all of the outcomes were the same, because there's only one way for that to happen. The only one way to happen is they have to be all diabetic, all not diabetic, right? When I talk about a certain number of outcomes out of a certain number of selections, out of a certain number of trials like this, 3 out of 10, there's many ways that can happen. It could be the first 3 people are diabetic, the next 7 are not. Could be the first one's diabetic, second's not, third one's is, fourth one isn't, fifth one is, and all the rest are not. Could be the first 7 are not diabetic, the last 3. There's many different outcomes, many different possibilities. So I can't look at it simply as this kind of event anymore. Okay. I go into this a little bit more detail with probability trees in that lecture, but I don't want to kill too much time on it. Make a long story short, this becomes a kind of a complex mathematical problem, because we have to really determine how many successful equally likely outcomes are there over what are the total number of outcomes that you could possibly have, right? So it gets a little complicated. There is a formula for this, and the formula looks like, what's that? Yeah, exactly. It's exactly that kind of thing. There it is. There's the formula. Okay, the probability this is on Blackboard. This is a particularly nice version of it because it's annotated. The annotation is a little blurry, I see, but I can make it a little smaller. That's okay, we can read. The probability of what's the probability of this particular outcome? The n in this situation is the number of ways that it can occur. X is the number of successes. Okay, where's X over here? Delete the probability. Yes. Okay. X is the number of successes, number of people, in our case, the number of people that are diabetic. N is the number of trials that we would be taking. In other words, we're going to select 10 people, and we're going to look for the probability exactly 3 of those 10 people are diabetic. So I'm going to call X the number of successes, the number of people that meet our criteria, and N the number of trials, the number of people that we're going to select. Don't feel bad about that. I have a cold. I have like a ton of cough medicine on me, and get some water and come back. Take a drink and come back. I have to sympathize because I've had this cold all week, and literally, I up until like I just doused myself in cough medicine, I've been coughing like every 3 seconds. So you can kind of hear it in my voice a bit still. So at any rate, okay, so that's what we're looking at here. So if you look at this, basically the way we calculate this, it's n factorial. That's the 10, 9, 8, 7, so on and so forth. N minus x factorial, that's 10 minus 3 in our case, 7 factorial, times x factorial, which is 3 times 2 times 1, times the probability of success, which is 0.1, right, to the third power, because we're looking at 3, and q is the probability of not having diabetes, 0.9. Okay, so, and then we're going to take that to the n minus x. So to be honest with you, if I just asked you what's the probability of given a prevalence of 10%, right? If I just asked you what's the probability of getting exactly 2 out of 3 people that are diabetic, be 3 trials and 2 successes, right? So what that would be 3 factorial, 3 times 2 times 1, over 3 minus 2, which is 1, which is just 1, times x factorial 2 times 1, times p, which is 0.1 to the x power, which is the second power, and this would be to the first 0.9 to the. You can actually calculate that. Wouldn't be a big deal for you. You can actually do that. If we're talking about a significant number of trials, this becomes, ridiculous to actually sit down and calculate. We're talking about, if we're talking about 50 trials, we're now talking about things where you're going to find things at a 49th power or something like that. It's not going to be really very practical to use this formula. We have a way around that, okay? And that way around that is to use a function that's actually built into Excel. Okay, so let's talk, before we go any further with that, we're gonna apply that in a second. What kind of variable am I describing here when I talk about a person being diabetic or not diabetic, or a coin flip, heads or tails? Binomial, exactly. Dichotomous or binomial can have 2 values, right? Yeah, and so it's categorical because it's, yes or no, diabetic, not diabetic, but it's also binomial. It can only have two values. Okay, so that kind of distribution, we can actually mimic that kind of distribution. Actually, let me go on with the calculations in Excel before I go any further with that, because I don't want to get too far off this topic before I lose you guys on this. Okay, let me get rid of that. So I'm going to open up Excel. So eventually it'll stop bouncing up and down and actually open. Okay, there we go. Yeah. Okay. Let me blow this up a bit so we can actually see it, even a bit more. Okay, that's good. That should be good. All right. So in Excel, as you know, there are many functions. We talked about Excel and the fact that it has hundreds of these special functions or applications that are built into it, and we access them. Typically, we access them in a cell by starting with an equal sign. Now, Excel knows that instead of a number or a label, I plan on putting a formula in there or some calculation in there. As it happens, this particular function is called binom, and it uses binom dist, and it uses a open parentheses. Once I hit open parentheses, it gives me a kind of a roadmap into what kind of information it wants going forward. Binom dist is basically just the calculation of probabilities using the binomial distribution. We're going to talk about that in a moment. Okay, so what is it looking for? It's telling me it needs the number of successes. That's basically the number of people or number of subjects or people that meet our objective, and the number of the number of trials, that's our sample size, and the probability of success, probability underscore S, probability of success for any one individual, in other words, prevalence, and comma cumulative. We're not going to worry about cumulative for right now. I'm just gonna say that you would put in either true or false, but we're not going to worry about that for the moment. So let's examine one of the questions I mentioned before. Given that the prevalence is 10%, diabetes prevalence is 10% in the population, what's the probability that we would have exactly 3 people that are diabetic in a sample of 10? If we randomly sample 10 people, what is the probability that we would get exactly 10? Well, let me ask you first, just think, it's just as a thought experiment. If the prevalence is 10% and I'm sampling 10 people, what would you think the most likely outcome for the number of people that are diabetic would be? How many? 1, right? 10% of the people, 10% of 10 people is 1 person. So you would expect that to be the most likely outcome. Would 0 be a likely outcome? No, 0 is not that big different than 1, right? Right? How about 2? 2 is not that different than 1, right? 7 might be really unlikely, right? Given that the prevalence only 10, likely we get 7 people out of 10 that are diabetic when the prevalence is only 10%. Doesn't seem very likely at all. So you might get 0, you might get 1. Most likely outcome would be 1, but 1 is not even going to be 50% of the outcomes, right? It's going to be the most likely. Let's just take a look at what the likelihood would be of 3 out of 10. Sounds to me like it's not going to be very high, right? Because it's pretty far from 1. Okay, so let's see what that's going to be. So the number of successes is going to be 3. We want to know what the probability for exactly 3 people is. Common number of trials is 10. Probability of success for any particular individual is 0.1. Any particular trial is 0.1. And I'm going to put false down here for cumulative. We'll worry about that later. And the probability is about 6%. The probability that we would get exactly 3 people out of 10 is about 6%. That's not 2, not 1, but exactly 3. Just that possible outcome. I'm going to examine this a little bit more closely. I'm going to put all the possible outcomes: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. I'm going to start with 0. Equals binomial dist, parentheses. And I'm going to say, instead of putting number successes as a number, I'm just going to click on 0. But it's 0. Since I clicked on that cell, it is 0. Times the number of trials is going to be 10, comma, the probability of success is going to be 0.1 for each individual person. And I'm going to say false for cumulative. I'm going to hit enter, and we're going to find out what that probability is. That's 35% chance of that occurring, right? Now, I'm going to try it for 1 now. But, you know, I don't have to do that. Again, I can just drag this down, and it'll recreate that formula down there using 1. And take, oh, in fact, 1 is more likely than 0. Not a whole lot more likely, but more likely. Let's do that again for 2. Well, it's still 20%. It's not nothing, right? Still 20%. Let's do it for 3. Well, we know what the answer is for 3. Whoops. We know what the answer is for 3 because we just did that. Okay, it's 0.5739, right? Okay, let's do it for the rest of these. Okay, so this is the probability for all of these other outcomes. Probability for exactly 6 out of 10 people being diabetic in this population, and if we took sample of 10 from this population, is 1/100 of 1%, right? 0.00, very unlikely, right? Probability of 10 people being diabetic is, well, look, it's basically 10 to the 10th power, 0.1, it's 1 over 10 to the 10th power. That's the problem, which is what we said, 0.1 times 0.1 times 0.1, which is basically what we said. What if I add all these up? What are they going to add up to? They're going to add up to 1 because this represents all of the possible outcomes. So all of the possible outcomes should add up to 1. And indeed it does. Okay, so now, very interesting that I said, what's the probability of exactly 3 or 4, so on and so forth. It's kind of a strange thing to ask. More likely something, let's say, for instance, if we're setting up a clinic and we expect to have 10 people coming into the clinic every day, and we want to know, well, how many people should we prepare for to be diabetic? We might want to know what's the probability for, say, up to 2 people being diabetic out of those 10 people, right? So what would up to 2 people represent? Up to 2 people would represent none, 1, or 2. So the probability up to 2 people being diabetic is going to be the sum of those probabilities. Okay, 93% chance that there would be only up to 2 people that are diabetic out of 10 on any given day if 10 people are walking in. Everybody comfortable with that, right? Okay, so now, what if I ask you what's the probability of 3 or more people being diabetic? Well, that would be the sum of all these probabilities. Probability of 3 or more is going to be about 7%. Right? Okay, well, that's very nice if I wanted to calculate the individual probabilities and then add them together. But if we were talking, if we were talking about a sample size of 63, that's going to get pretty tedious, right? Well, there's another way I could have used this. For instance, what if I wanted to know what's the probability of 3 or fewer people being diabetic? 3 or fewer. Okay, so equals binomial dist, parentheses. 3 is my successes, 3 successes, comma, trials 10, comma, probability is 0.1. And now instead of saying false, I'm going to say true for cumulative. And what's that going to do for me? It's going to give me the probability, the cumulative probability for 3, 2, 1, and 0, which is 98.7%. So I didn't have to go through each individual one. What's the probability for more than 3 being diabetic? Well, if this is the probability for 3 or fewer, right, then probability for more than 3 is going to be equal to 1 minus this. Everybody comfortable with that? Yes.
Are not independent.
These are independent. In other words, well, each individual person is independent of one another.
Okay, so why are you looking at it as some probability instead of
Because I can only multiply it when it's the same likelihood, the same outcome. In other words, I know that that's the only, let me show you, for instance, let me go back a little bit, and I was hoping to avoid this, but I think maybe, now that I realize that question has come up, I realize why very frequently I do this first. Let's take our coin flip, right? Remember our coin flip? We said the first time we flip a coin, it could be heads or tails, right? Okay. So if it's heads or tails, it's a 50% chance of heads and a 50% chance of tails. First coin flip. If it comes up heads, what could the second coin flip be? Could be heads or it could be tails. Second coin flip, first coin flip came up tails. The next one could be either heads or tails. Okay, so it's probability heads. Probability I get heads again is 0.5. Probability I get tails is 0.5. Probability I get heads here is 0.5. Probability I get tails here is 0.5. What about the third coin flip? Well, probability, let's see, if I get heads and then heads again, probability the next one doesn't know that, it's independent. So probability getting heads again is 0.5. Probability getting tails is 0.5. Probability of, if it were heads, tails, probability next coin being heads is 0.5. Probability of being tails is 0.5. Similarly with all of these others as well. Heads, tails, tails. Okay, so how many outcomes do I have here? I have 1, 2, 3, 4, 5, 6, 7, 8 possible outcomes. I could have 3 heads here. I could have heads, tails, 2 heads. I could have heads, tails, heads, 2 heads. I could have heads, tails, 1 head. I could have tails, heads, 2 heads. I could have tails, tails, 1 head. I could have tails, head, 1 head. And I could have tails, one head, no heads. How many possible ways are there out of 8 of getting 3 heads? Only one way to do that, right? All of them have to be heads. So the probability of getting 3 heads is 0.5 times 0.5 times 0.5, which is 0.125, which is also one possible outcome out of 8 possible outcomes, which is also 1 over 8 is 0.125. Similarly with 3 tails, 0.125. What's the probability of getting 2 heads? Well, there's 3 ways out of 8 to get 2 heads, right? 0.5 times 0.5 times 0.5, 0.125, 0.125, 0.125, which is 0.375. That's the probability of getting that outcome. And the probability of getting the outcome of 3 tails, 0.375 as well. And amazingly, when you all these add, again, you add up to 1. So the reason why it worked to multiply them was only the fact that they were all the same outcome. They were all tails, all heads, all diabetic, all not diabetic, all insured, all not insured. Right? Otherwise, we would have to go through a tree like this with the diabetics, right? For the first diabetic, 0.1 diabetic and 0.9 not diabetic. And then the next one could be diabetic or not diabetic, 0.1, and so on and so forth. As long as we go up there and they're all diabetic, it's just be 0.1 times 0.1 times 0.1. As long as we're only dealing with the non-diabetics, it'll be 0.9 times 0.9. So anything in between, any numbers in between, would be dependent on what the possible, all the different possible combinations could be of outcomes, right? Just like when we throw a die, when we roll a dice, right? There's 6 numbers on the dice, 6 numbers on the second dice, right? So the 2 dice don't know what the outcomes are together. So literally, if you want to know what the odds are, you have to look at what all the possible outcomes. You could get a 1 and a 1. You could get a 1 and a 2. Get a 1 and a 3, and so on and so forth, and go through all of them. You'll find that there are more ways to get 7 than there are to get 2 or 12. How many ways you think you get 2 or 12? Only one way to get 2. They both have to be 1. Only one way to get 12. But all the other numbers, there are many ways to get 7. There are many ways to get 6. 2 and 4, 3 and 3, 1 and 5, and so on and so forth. So as 1 and 1, there's only one way for that to happen. Right? So the odds of getting a 1 when you throw 2 dice are 1 in 36. Okay, what are the odds of getting 11? How many ways are there to get that? You get a 5 and a 6, or a 6 and a 5. Only 2 ways. Out of how many ways? 36 possible combinations. 6 times 6. 30. So that's 2 out of 30. That's 1 out of 18 is the chances of getting an 11. Right? Anybody know what they call that on the craps table? You ever go near a craps table and somebody yells like "yo"? That's yo. You hear yo, that means an 11 came up, right? And what are the payoffs? People love betting yo. Why do they love betting yo? What is the payoff for yo? It's 15 to 1. Now that you know that the odds of it coming up are only 1 in 18, is 15 to 1 such a good bet? No, it's an exciting bet because it pays off big, but the odds of it coming up are much greater than what the payoff is. It's one of the worst bets on the table, right? So, but I mean, that's how these combinations, that's how this works. I don't want to get too buried in this stuff. For the moment, please take my word for this, okay? I don't mean, it's not really fair for me to say that, but, rather than brush off if you're not comfortable with that. But did that help at all? I mean, right, exactly. It only worked that way with all diabetics, or they all satisfied the same condition because the binomial outcome was the same thing, like heads coming up all the time, right? There's only 2 choices. Okay, so let me get my thoughts together here. Okay, let's see. Okay, so let me open this up. Now, let me show you something interesting. Now, very frequently in nature, these kinds of outcomes, binomial outcomes, you'll notice that when we talked about when I talked about the dice, the most common outcome was 7, because there's more ways to get 7 than any other number. 6 and 1, 1 and 6, 3 and 4, 4 and 3, 5 and 2, 2 and, there's more ways to get 7 than any of the other numbers. That's the most frequent outcome. Now, with the binomial distribution, okay, if we were to say to ourselves, let's say I wanted to toss 100 coins, right? And we know that the chances of heads coming up is 50% on each one of those coins. If you toss 100 coins, how many heads would you typically think would be the most likely outcome come up? 50, right? Okay, 49 and 51 out of 100, you toss 100 coins, wouldn't be an unusual surprise to get 49 heads or 51 heads, 47 or 52, 53, 46 or 54. Those wouldn't be that unusual. But as you got further away from what the most likely probability is, 50, you would expect that to come up less and less frequently. That to be less and less likely an outcome. Okay, and indeed, that's what we can do. We can actually physically demonstrate that that's true. So let's take an example of the coin. Some outcome that is 50-50. Okay, let's see if we can't invent a machine that will demonstrate that for us. Okay, so here we go. What we're going to do is we're going to drop marbles into this machine. The marble is going to come down. It's going to be funneled down into this area here. It's going to come down. and it's going to hit a little post. It's like a pinball machine or pachinko. And anybody know what a pachinko machine is? You know, I asked the other coach, nobody knows it. You know what a pachinko machine is? A pachinko machine is basically a Japanese pinball machine. Doesn't work exactly the same way. They just come, it's kind of a gambling thing, and it sits vertically, and the balls come down, and they oh, no kidding, really, yeah. So, yeah. Oh, okay, good. There you go. So the marble comes down. The marble comes down and hits its first post, right? That it can go either left or right. So chances of it's going, if the post is perfectly in the center, chances of it's going left, same as chances of it's going right, just like a coin being heads or tails, right? So it's going to go right or left. It bounces off, it goes left, then it comes to the next post. Again, left or right. So presumably by the time it gets to the bottom, the most likely outcome is for an equal number of lefts and an equal number of rights, right? Just like heads, a coin coming up. So we would expect these balls to be more accumulated in the middle than in the ends. In fact, we would rarely expect to see a ball go left, 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 and just make all left turns and wind up at the very end. That wouldn't be a very likely outcome. That's exactly mimicking what we're seeing here with the binomial distribution. Well, in fact, there are such machines. They're called Galton machines. They were invented by or first developed by a statistician by the name of Galton. This one is located at the New York Hall of Science, which is in Queens. Anybody ever been there? It's like Flushing Meadow Park. It's great for kids because there was some demonstrations and stuff like that, hands-on stuff. This is literally a Galton machine, and what you can see here is you can see these balls coming down and hitting the pins and bouncing in either direction. And as we scroll down here, as we go down to the bottom, you'll notice that they have sketched out a theoretical binomial distribution. You can see the balls literally accumulating in there. And this kid in the back, yeah, he's going to turn around and he's going to look at this. He's hanging around there because he wants to see what happens when it fills up, and then flushes out or something like that. But he was hanging around there for quite a while. So at any rate, so that's a physical demonstration of this is how things work. This is not our imagination. Okay, and this is basically a binomial distribution. Okay, so now they don't always look that neat. For instance, if I plotted the results of our binomial distribution for diabetics, problem with our situation is that the probability, most likely probability is here 1, 2, 3, 4, up to 10, and so on and so forth. It's going to be kind of weird because 0 is kind of frequent. It's going to look something like that. It's not going to be a real nice bell-shaped curve. But if it was 50%, right? If it was 50% or 40%, it might look more something like that, like what we were seeing there, right? So our particular one wouldn't be that's quite as pretty because it's bound on one side by 0. Can't go below 0. Can't go below 0 out of 10, that is. Okay, so binomial distribution. So now, let me do a problem or two that involves a binomial distribution. Okay. Okay, let's do this one. A study, now, first of all, I have to preface this. This is, first of all, an old question that we made up, right? And you can see, obviously, I'm 4 generations behind. A study indicates that 4% of American teenagers have tattoos. Anybody know what the real number is? Somebody want to take a guess? What percentage of American teenagers think have tattoos? Give me a guess. Huh? Okay, let's look it up. What percentage of American teenagers, yeah, up to 18, have tattoos. How do you spell tattoos? T-O, I spelled it wrong. It'll correct it for me. 38, it's unclear how many times have tattoos. Said about 38% of young people, oh no, hang on a sec. It says 18 to 29. 38% have at least one tattoo. Huh? Is that unbelievable? And now when I wrote this question 15 years ago or something like that, what did I think it was?
4%.
Right? Things have changed, let me tell you. But at any rate, I wonder if they have tattoos now. Could be. So at any rate, so let's see what we have here. Still, we're going to use the number that we have here. Study indicates 4% of American teenagers have tattoos. You randomly sample 30 teenagers. What's the likelihood that exactly 3 will have tattoos? How are we going to solve that? Right. Well, if we use that formula, we would have to use n is equal to 30, x is equal to 3. We would have to use p is equal to 0.04, q, which is 1 minus p, is equal to 0.96, and we'd have to be taking things to like the 27th power and so on and so forth. Not very practical. We're going to use the binomial distribution function in Excel. So binom dist, parentheses, and again, it's going to ask me number of successes. Number of successes is what? 3. Number of trials is 30. Good. 30. The probability of success for any individual is 0.04. True or false for cumulative? Question is exactly 3 will have a tattoo. True is cumulative. True will give it a probability for 3, 2, 1, and 0 combined. Are we asking for that? No, we're only asking for that. Right? So false. Good. And that's the probability is about 9%.
Can you see the question? Yeah.
Oh yeah, I'm kind of like buried that. Okay. Okay, let's see if I can't slide the Excel sheet down a little bit.
I was going to ask, could you explain when you would use the true and when you would use the false?
Sure. You would use the true when you wanted to know. Remember that true or false is an answer to the question cumulative probability. Cumulative. So if the question is, what's the probability exactly 3 of your 30 will have a tattoo, just exactly probability for exactly 3 only, right? Then that is false for cumulative. You only want that probability exactly. If you put 3 true there, it will give you the cumulative probability for 3, 2, 1, and 0 people having tattoos out of 30. Right? So in other words, combine all those probabilities together. Okay. But in this case, I'm not asking, I don't want to know what's the probability for 3 or fewer people having tattoos. I only want to know probability for exactly 3. So I would put false. If I look at the next question, for 3 or fewer,
Then that's true.
then that's true, right? Binom dist, parentheses, and number of successes is 3, comma, trials is 30, comma, probability is 0.04, comma, true now is going to give me the probability for 3 or fewer, 3, 2, 1. Okay, bingo, that's 97%. Okay, probability of 4 or more that will have tattoos. Well, that's the probability of 4, 5, 6, all the way up to 30. Right? Well, hang on a second. Problem is only works going down, not going up. In other words, if it only gives you the probability. What am I going to put in there? Am I going to put in 30? Right, 1 minus. Right. So whatever. If the probability of having 3 or fewer, 3, 2, 1, or 0 is 0.97, what's the probability of having 4 or more? Is going to be 1 minus that, right? So this is the probability for 3 or fewer. So the remaining is what's the probability for 3 or 4 or more. Oops.
Okay, I don't know if you've ever asked this one, what happens if instead of C or you had a D and it said 7 or 1? Then you can't do a 1. How would you do that?
No, you can just, what you would do, if I asked you for 7 or more, right? what you would do is 6 cumulative, yes for true for cumulative, and then subtract that from 1. Right? In other words, I'll just answer the question you just asked. What's the probability of 7 or more is equal to binomial dist, parentheses, 6, comma, 30, comma, 0.04, comma, true. That'll give me the probability for 6 or fewer. And then just subtract that from 1. Will be 7 or more, right? Right? And you got to parse it a little bit because you could make it a little confusing. What's the probability of more than 4? What's the probability of more than 4? Well, wait a second. Probability of more than 4 doesn't include 4. So that would be a probability of 4 cumulative minus 1 because you only want 5 and up. So just think about the question. What are we actually after there? Right? See the difference when I was using that? Okay. Okay, so that's really, as far as binomial distribution, I think that for the most part, that's probably as complicated as we're going to get. So now the only other thing I might want to bring up, and I probably won't turn up on a test or anything like that, but just so you've been exposed to it, you've heard of this. I'm sorry, you were going to ask me a question?
No, I was going to clarify. So for the example you gave was 7, but I think you said 7 or more, right? Not more than 7.
7 or more, right?
But if you said more than 7.
More than 7, I would have said 7 down, right? And then subtracted from, more than 7 is 8 and up. Yep. Yeah, just think about the question, what we're really asking for. Okay, so the other thing that you might want to be interested in is that if I have, like with our coins, if the probability is equal to 0.5, right? Well, if I take a sample size of 100, right, with our coins, the distribution that we just saw before, I know that I'm going to get this kind of almost bell-shaped curve that we saw with that Galton machine, right? Where the middle value is like 50 coins, 50 heads, for instance, if we're talking about if we're talking about flipping coins, flipping 100 coins, how many times will we get heads? If I did that over and over and over again, the most common outcome is I would get 50 heads out of the 100 coins. Okay, so now, and then I would get other numbers of heads, like 48 heads or 47 heads or 53 heads, are going to be somewhat less common than 50 out of 100. Okay, so, but the thing is that this takes an unusual kind of unusual bell-shaped curve. Looks very similar to something called a normal distribution. Okay, and these normal distributions have certain properties. One of them is that you have a mean. For instance, in other words, if we did this many times, half the time we would get fewer than 50 or fewer, the other half the time we'd get 50 or more heads, right? Probably be bad. If we took it hundreds of times we did this, then half the time we'd get 50 or fewer, half the time we get 50 or more. So there's kind of some central value that we're going to have. And we can actually calculate that mean for this distribution by saying the sample size times the probability. So the average outcome, if we toss 100 coins and there's 50% chance of getting heads, then the average outcome would be 0.5 times 100 or 50 heads. That would be our average outcome. What if we only tossed 10 coins, right? What would the average outcome? The average outcome would be 10 times 0.5 would be 5 coins out of 10, right? So we can predict that this kind of binomial distribution would kind of mimic a normal distribution where the mean number of probable outcomes for that probability is going to be the middle of the distribution, the mean of the distribution. If we were dealing with a probability like probability of people being left-handed, right? That might be, the probability of being left-handed might be 30%, right? If I sampled 100 people, what would be the average number of, average outcome for a group of 100 people with a probability of 30%? It'd be an average of 30. Half the time we would get more than 30, half the time we would get less than 30 if we repeated this outcome. This is called the normal approximation to the binomial distribution. There's another factor to this, and that is, you remember in the beginning, first week or two, we delved into calculating certain ways of predicting or describing the variability of distributions, of samples and populations. And one of the things we talked about was the standard deviation. Okay, you can actually approximate the standard deviation as being equal to the square root of, I'm going to have to try and remember this now, P times Q divided by N. I'm having a senior moment here. P times Q times N. So for 50%, it would be 0.25 times 100 to be 25. Yeah, P times N times square root of P times Q times N. Q is 1 minus P. The probability, P is probability of success, Q is the probability of not success. Like for instance, diabetes would be 0.1 and Q would be 0.9 times the size of your sample, which is N. And that would give you the standard deviation from the number, the variability in the number of outcomes that meet that criteria. Don't worry about that for now. We may get to that later on in the semester. We may talk about it again, but we're not gonna worry about that for now. Instead, we're gonna move on to actual normal distributions. But you may get questions on the exam, for instance, on how to calculate these binomial probabilities. Okay, but they're pretty straightforward. What's that?
So why not say
It really is. If you look at the distribution for the binomial distribution, they're really not perfectly normal. Okay, we're going to talk about situations where they are perfectly normal now. Let's talk about normal distributions. Okay, so in nature, many things distribute themselves in a way that through chance that follow a certain pattern. And that pattern is very frequently is described as what they call a normal distribution. So for instance, if I were to describe the distribution of, let's say, height among boys from 5th grade to 6th grade, 5th to 6th graders, and a distribution of height for boys. Well, the average height is going to be, I'm going to make a number up. The average height is going to be maybe 50 inches tall, right? So if I have a large number of students, and I would expect that the most probable outcome when I measure their heights is going to be 50 inches. There's going to be a lot of students that are 49 inches tall. There's going to be a lot of students that are 51 inches tall. There's also going to be many that are 47 and 48 and so on and so forth. But as we get further and further away from that average or that middle value for the heights of these children, right, we get fewer and fewer children that meet that criteria. Excuse my voice, I'm getting over a cold as we were just talking about. Did she not come back? I guess that's because the coughing. Now that I mentioned, I feel badly. I because I know that I have the same problem. So at any rate, God, I know, you get a drink of water and sometimes it goes away and stuff. So at any rate, so we often see this kind of distribution in nature. right? So if we get a large enough sample and these bins are small enough, in other words, instead of 50 inches, it's exactly 50 inches or 49.9, and these bins get smaller and smaller and smaller, we can start to see that these can be joined together and eventually approximate this unique kind of curve. It's a bell-shaped curve. And one of the unique properties of this normal distribution curve is that it's symmetrical. The mean, it's usually you associate this with numerical variables. So the mean is in the center of the distribution, and it's the same as the median. The median and the middle value and the average value are the same. The two sides of the distribution are symmetrical. You can fold one over onto the other, and they would match identically in a perfect normal distribution. That's what we would expect to see. Okay, well, in addition to this typical shape and this idea that they are symmetrical, there are other properties that the normal distribution has that are important to us. Right? First of all is that the mean is in the middle. That's important to us, right? When I use the term mu, we know I'm referring to the population mean, right? When I use X bar, I'm referring to a sample mean. So this, for the time being, I'm going to talk about population means, mu. So now, the other thing that we understand about mu, and the other thing that made that standard deviation, that calculation that we learned earlier, that measurement of variability called standard deviation. Again, standard deviation is for the sigma, is for the population. And when I say just S or SD, that's for a sample. So I'm going to be working with sigma here, population standard deviation of population. That standard deviation has special application in a normal distribution. Okay, there's certain properties normal distributions have. Okay, and among those properties that are related to standard deviation is that, okay, if I have a mean, say the mean is equal to 100. Say the standard deviation is equal to 10. So if I look at this standard normal distribution, if this is 100, if I go one standard deviation below the mean, what would that value be, one standard deviation below the mean? 90. And let's say this represents blood pressures of people in a certain population. Okay, if I go one standard deviation above the mean, which would be blood pressure of 110, right? Okay, so I'm one standard deviation below the mean, and I'm one standard deviation above the mean. The area between these two is approximately 68% of this represents about 68% of this population. A couple of ways I could look at this. I got to look at this and say, oh, represents 68% of the population. I could also look at it another way and say that the probability that I would randomly pick a person from out of this population that has a blood pressure between 90 and 110 is 68%, 0.68. That makes sense because 68% of the population is between there and there. That would suggest that that's the probability I would pick someone out that would wind up in that range.
How do you know that?
I just know. Trust me for a moment on this.
Okay.
Okay. It's in fact a rule that we're going to assume is true. It's called the empirical rule. Okay, I'm going to go a little further out, and I'll give you more of I would certainly give you more of a factual reason for knowing that's true in just a moment. There's actually a formula that this normal distribution is based on. Okay, so if I go further out, if I go out two standard deviations, 80 and 120, okay, the area of this distribution, remember this area represents the proportion of the population or the probability that any individual is in that area, is 95%. If I go out three standard deviations, which would be 70 and 130 in this case, that would represent up to 99.7% of the population. These numbers represent something called the empirical rule. I'll give you a better picture of it right behind here. Where does that all come from? There's actually remember, if the mean is, if we know that this is a normal distribution, that it's distributed, like whether any individual you pick is below or above the mean, it's just random. They could be below or above the mean. It's just chance whether you pick them below or above the mean. Well, there's a formula that you can use that represents that. And I can't find it. Yeah, that'll do. Oops. Here's the formula. This formula gives you the height of this curve at any point from the mean to the left or any number of standard deviations to the left or the right of the mean. And this is based on a couple of constants, e, natural log, pi, and just what the mean and the standard deviation are. So if you're looking at the mean, well, the mean and the value that you're looking at, the particular value, x is the value that the location on there. Let's say you're looking at the mean itself. That would be 0, basically, right? So this would be eliminated. This would be a 1, and then you can evaluate this. But any other point on here, you look at the value of x, say the blood pressure, minus the mean blood pressure. And you could find this exponent and figure this calculation out. Long story short, my voice won't take a longer explanation. That formula represents the height of this curve at any point. And from that formula, you can actually develop tables that help you understand what these areas represent, to help you calculate what these areas are. Okay, so for instance, this is our empirical rule. This is an estimate based on whole numbers for the standard deviation. Now, I told you, I lied slightly. I told you that one standard deviation on the other side of the mean is 68%. Well, a little better estimate would be 68.2%. It's still an estimate, though, still not exact. And two standard deviations would be 95%. In fact, it's like really a little bit more like 96, 95.5% or something like that. But that's roughly close to what you would expect, about 95%, 99.7%. Let's take a look at a possible way that you might apply this. Okay, so assume the heights of adult Caucasian men have a mean of 68 inches and a standard deviation of 4 inches. What's the probability that a randomly chosen individual from this population has a height greater than 68 inches? We're not going to need a piece of paper for this. Think about this for a second. The mean is 68 inches. Standard deviation is 4 inches. What's the probability that a randomly chosen individual is greater than 68 inches? What's the mean? Right, what's the probability somebody's taller than the mean? That's half of the distribution, right? 50%, right? What's the probability it's less than 68 inches? 50%. What's the probabilities between 64 and 72 inches tall? How many standard deviations is 64 below the mean? 4 inches. How many standard deviations? Right, standard deviation is 4 inches. So it's 1 standard deviation below the mean to 1 standard deviation above the mean. And what does our empirical rule tell us about that? Where'd it go? I lost it. Well, it's 68%, right? Because remember, it's minus 1 standard deviation, 4 inches. It's 64 to 70. What was it? 72. Yeah, between 64 and 72. 1 standard deviation below to 1 standard deviation above. That's 68%. Okay, everybody okay with that? Okay. Sure. What's the probability that a randomly chosen individual from this population has a height between 64 inches and 72 inches? Okay, so 64 inches would be 1 standard deviation below the mean, 72 will be one above the mean. So the probability he would be in this group here is 68%. How about probability between 60 inches and 76 inches? How many standard deviations is 60 inches below the mean? 2, right? And 76 is 2 above the mean. So that would be about 95% probability that a randomly chosen individual would be between those two heights. What's the probability that he would not be between those two heights? That he would be shorter than 60 inches and or taller than 76 inches? Well, 95% chance he's going to be between those two heights. So what's the probability that he would be shorter or taller than that? 5%, right? Only 5% left. Right, 2.5% on one end, 2.5%. 2.5% chance he would be shorter, 2.5% chance he would be taller. Remember, these are all round numbers. They're not perfectly accurate. Okay, assume the heights of adult Caucasian women have a mean of 63 inches and a standard deviation of 3 inches. What percentage of the women in this population have a mean height greater than 63 inches? Mean of 63 inches, standard deviation of 3. What's the probability that they have a height greater than 63 inches? 63 inches is the mean, so 50%. 50%. Greater than 66 inches. Oh my goodness. Let's sketch that. Hang on a second. Okay, so I'm going to draw this 63 inches and a standard deviation of 3 inches. That's a pretty nasty looking curve. Okay, so the mean is, what I said the mean was here, 63 inches and 3 inches. 63 inches and the standard deviation is equal to 3 inches. And we want to know what's the probability that she has a height greater than 66 inches. So 66 inches. How many standard deviations above the mean is 66 inches? It's plus 1 standard deviation, right? Okay, so let me use the empirical rule. Do I know what the area in here is? How much is that? That's 34%. So what's the probability that she would be taller than 66 inches? How much? Yeah, 16%, right? Because 50% is to the right of the mean. Everybody okay with that? Right? Okay, next one. Less than 60 inches. What's the probability that she would be less than 60 inches? What is that? That's minus 1 standard deviation. So what's this area in here? Less than 60 inches. It's the same as the 16% at the top. Why? Because it's symmetrical, right? This would be 34 also. Okay, what am I doing here? I'm just manipulating the way I'm using this empirical formula. I'm just playing around with it. Okay, now I'm going to do one more. Okay, I'm going to use this one right here. We got a fresh piece of paper here because I'm going to want to draw this. Okay, assume that the heights of adult U.S. women have a mean of 63 inches and a standard deviation of 2 inches. I'll sketch that. But very often you're going to wind up wanting to sketch these things. It's a mean of, what did I say it was? 63 and standard deviation of 2. Okay, so the mean is 63 inches and the standard deviation is equal to 2 inches. Okay, so let's see. What percentage of women you expect to have a mean height less than 63 inches? That's an easy one, right? 50%. Okay. Less than 62 inches. Okay, less than 62 inches. Uh-oh, I got a problem here. 62 inches, the standard deviation, how many standard deviations below the mean is 62? It's half of a standard, right? Well, you want an easy way for me to calculate this. 62 is pretty easy because I can see it's only 1, standard deviation is 2. It's only half a standard deviation. Not always going to be a nice, easy round number. So many times we will refer to the number of standard deviations on either side of the mean as a z-score. Number z represents number of standard deviations. So I'm going to say Z is equal to the difference between the number you're interested in and the mean over the standard deviation. So what's that going to be? In this case, 62 inches minus 63 over 2 is equal to 0.5. Sure. The Z-score represents the number of standard deviations away from the mean. And the way I calculated that was just the difference between the value you're interested in and the mean. So in this case, it's 62 and 63. It's a 1, right? Okay, a -1 because we're to the left, So if I use this formula, it helps me keep the signs right. So 62 is the number of X, represents the value I'm interested in, the height I'm interested in, minus the mean over the standard deviation. It's just the difference between the mean and that value over the standard deviation. And it gives you the number of standard deviations away. 62 minus 63 is -1. So divided by 2 is -0.5. Right? -1 divided by 2 is -0.5. The negative part only means that it's to the left of the mean. If it were 64 instead, it's the same difference, except it would be 64 minus 63. It would be it would be 1 also, but it would be a positive 0.05, right? 0.5. Positive 1/2. 64 minus 63, 1 over 2. Standard deviation, which is 2. Okay, so we need to know what this area is, but the empirical formula is not going to help us here, is it? We need some other device that'll give us a better read or more accurate read on what these, more versatile read on what these standard deviations are, on what these areas are in the distribution. And we have that. There is a table called the Z table, appropriately enough, right? Okay, it's on Blackboard. It's in your book also. In the back of your textbook, there is a table of areas for standard normal distribution. Okay, so I tend to use one that's came out of a book called Agresti, but it's basically identical to one that's in the textbook. Where'd it go? I got the wrong folder here. I think it's, what's that? They're all the same. When I say they're all the same, the numbers you get from them are all the same. The layouts could be a little bit different. I'll point out to you why the layouts may be different. Let me find it here. There we are. And normal distribution. No, okay, nope, it's not the one I want. Agresti, here it is. Okay, there we go. So let's see what I have here. Here's standard normal distribution. What I have here is in this left column is the z-scores. Notice these are all negative, -3.4, and it goes up to 0. A z-score 0 is the mean, right? Not surprisingly, the area that's represented by a z-score 0 is 50%. What does that mean? If you look at this little graph up here, what it's telling you is that this table will give you the shaded area for any z-score that you want to know. So the z-score that we want to know is -0.5. 0.05, -0.05 is 30.3085, right? So in other words, a z-score of -0.5 represents a shaded area of 0.305. Now notice that there are two tables here. There's the negative numbers and the positive numbers. And you'll notice that the positive numbers are to the right of these. Again, give you the area to the right of the z-score, which is a positive number. So all of them are going to be above 50% because it's always giving you the area below that. Just like the binomial distribution, cumulative gives you the area below. This gives you the area below. So in our case, 30.85 or 0.3085 is our answer to that first problem. Yes.
So weird. I learned this in high school. I have no idea what I'm doing. So the first column is a 0, 0
Hang on a sec, on that table?
on the table. Why did you pick that?
Okay, because the way this table is laid out, I was going to wait until the next problem to show that to you. The way this table is laid out, let's say I wanted to know what was the z-score. Let's say our z-score came up negative 1.36, right? Well, negative 1.3 is here. Negative 1.30 is represented by an area of just a little under 10%, okay, to the left of that z-score, 0.0968, right? However, what about if you had the next digit, negative 1.31 or 1.32 or 1.33 and so on? You don't want to go through a column of numbers that's like 1,000 numbers long. So what they do is they put the next digit in the next column. So negative 1.30 is this area. Negative 1.31 is this area, 32, 34, 35. So it's basically each column represents the third digit in your calculation. Right? So, okay, so we're going to get to another version of this in a second. No problem. Well, I mean, we're going to get to it anyway, right? Okay, body temperatures. Now, I've been taking my temperature all freaking week, so this is a good problem for us. Okay, the body temperature doesn't have a mean of 90. I don't even know if that's true. 98.6. That's common. That's common wisdom. It's probably not really true, right? Okay, and a standard deviation of 0.6 degrees Fahrenheit. Find the probability that a randomly selected individual has a mean body temperature greater than 99 degrees. Okay, so let's see how we would solve that. So first thing I'm going to move this over so we can get to it. And then I'm going to get to this and see if I can't get a fresh page to write on. I do like drawing this every time. I think it helps you if you draw it. Okay, so now let me go back to our problem. And our problem said greater than 99 degrees. Okay, so 98.6 and 0.6. So our distribution looks something like this. .6 is the mean, and the standard deviation is equal to 0.6. And we want to know what's the probability of greater than 99 degrees. So 99 degrees is not that far above the mean, not too straight, not that far above the mean. 99. So what's the z-score? What's the z-score for 99? Z-score is 99 minus 98.6, right? Everybody agree with that? Divided by 0.6, which is equal to 0.4 over 0.6, which is equal to 0.67, right? Okay, so now if I wanted to know what's the probability that you would have a temperature higher than that, we're talking about this area in here. Which area does our table give us? It's to the left, right? So we're going to have to find that area and then subtract it from 1. Okay, let's go to our table and see what positive 0.67 will give us. Right, it's a positive number. So we know it's going to be above 50%. Positive 0.06, 0.060 is 0.77257. 0.061, 2, 3, 4, 5, 6, 7 is 0.7486. So this side is 0.7486. So that leaves on this side 0.2514, 24.14%. Probability you have a temperature greater than 99 degrees is 0.22514, assuming that this is really true. Standard deviation really is 0.6, and that the mean is really 98.6. I think it's probably lower than that. The standard deviation probably not that great. Okay, but at any rate, that's how we would apply this. Okay, so I'm trying to think if we need to do one more. There's something else I want to cover before I give up on this. There is one other thing I want to bring up. And I don't think I covered it enough to really put it on the exam, but maybe it'll carry over, I guess. Okay, let's see. Okay, let's look at this problem. The blood pressure readings in some population, I'm not going to go into what population, have a mean of 120 and a standard deviation of 8. What blood pressure would you expect, would you have to exceed to be in the highest 10% of this population? That's an interesting question. Okay, so I'm going to sketch that out. And I'll finish up with this example. And again, this particular question I won't put on the exam because we didn't get a chance to have much of a chance to really cover this. It'll hang over to the next one, I guess, or maybe you'll escape it. Okay, so let's take a look at this distribution. What do we know about this distribution? The population mean is 120. Anybody recall what the standard deviation was? You guys have worse memory than I do. Right? Is 8. Standard deviation is 8. And we want to know, what does your blood pressure have to be for you to be in the highest 10% of this population? Right? That would be where this area is equal to 10%. Right? So how are we going to figure that out from what we know? Well, the issue here is that we know we want this area to be 10%, but we don't know what that z-score is. Right? Okay, let's use the table to work it backwards. Let's look what area that we need, what z-score do we need for this area here to be 90%. I'm going to go to my tables. Okay, and I'm going to look through all of these areas. First of all, I know it's going to be on the positive side, right? Because 90%. I'm going to look into these areas. I'm going to look to see where it's 90%. 1.3, how about 1.2? How about right here, 1.29, right? 0.8997. That looks as close as we're going to get. So it's 1.29 is the z-score that we need. So this z-score, if this z-score is 1.29, then anybody above that is in the top 10% blood pressure wise. But what blood pressure is that? Remember that? Yeah, what's that? Exactly. We'll use our formula for that. Remember our formula, z is equal to x minus mu over sigma. We know what sigma is, we know what mu is, and we know what z is. So we should be able to calculate what x is, right? What that value has to be in order for z to be equal to 1.29, right? So let's see, 1.
Is that z value 1.29? Is that representing the 90% that's not in that?
Yes. Yes, doesn't matter, same thing, right? In other words, that z-score represents 90% is below that, but that leaves 10% above it. So it's the same z-score. It's a z-score that represents the top 10% and the lower 90%. It's the same point, right? Okay, so let's see this. Is equal to x, which we don't know, minus mu, which is 120, over sigma, which is, what was it? 8. Good, thank you. Somebody remembers it.
Can you move your thing over?
Is it blocked by something? Yeah, I don't know. Yeah, I don't know. Oh, I never moved that out of the way, did I? Okay, no problem. Okay, all right, so I can cross multiply here, right? Put this over 1 and cross multiply. So what does that give me? That gives me 1.29 times 8 is equal to x minus 120. Everybody comfortable with that algebra? Okay, so x is equal to 1.29 times 8 plus 120, which makes sense because I'm adding something to the mean. I'm adding that distance that represents that z-score to the mean. What does that come out to be? .29 times 8 equals that plus 120. equals, so if you have a blood pressure of 130, right, you're in the top 10% in this population for blood pressure. So, I mean, where would you use something like this? You would say to yourself, oh, we're with the CDC and we recommend that doctors, when they screen for blood pressure, that they start treating with statins, blood pressure medication, if you have blood pressure again over 130. What they're saying is that that'll be the top 10% of blood pressures. And so it's pretty handy. I mean, you can see that there's going to be application for this in public health and in a lot of other things. Okay, that's about it. Now, my voice is a little bit better on the other recording, but it's not perfect. It's not perfect. That was like just a couple of days ago, so it's not perfect there either. But you might want to play both if if it doesn't drive you crazy, because I may have expressed things a little bit differently that might be a little bit clearer to you on that other one. I definitely went over the idea of these probabilities and these different outcomes, the binomial distribution, a little bit more detailed in that version. I had a little bit more time to do it. Okay, guys? So like I said, on Thursday, rather than meeting here, I may be here anyway. I don't know. I have a lab that I do here. But I may be here. I may either be here broadcasting in another room or something like that. But my intention is that either then a session like this to introduce new material, what I will do is that anybody online or here or any of the other students that are taking the course, if they have questions on the material up to this point, on the homeworks up to this point, that they can post questions on the discussion forum on Blackboard, and I'll address those in preparation for the exam. Maybe even do a little bit of, if I don't get many of those, maybe I'll do my own version of preparation for the exam. Okay, guys? All right, good. So I will do it exactly the way we had described it. Right, 2 tries. Yes, I'm sorry. Yeah, it's basically due the same. It's due on the 3rd, which is Thursday, yeah, same day as I post the exam. It's going to be that way because that's material that's going to be on the exam, right? So it makes sense to do it before the exam. Okay. On the homeworks, though, you can collaborate with one another on homeworks, no problem. As long as you submit the homework before October 3rd, at least one try, you can come back anytime you want and redo it.